Okay, good morning. So we're using the big screen today. So people might appear fatter than they usually are on the screen. First a reminder. So the first midterm is like 8 days from now. What? Yeah. So it's going to be on February 11th on the Wednesday from 6:30 to 9:30. I'm not sure. Is it in the same room as the homework writing session? Yeah, okay. So it's probably going to be in that room. And it covers lectures 1 to 6, which means the first 3 weeks of the course, or you can also think of it as the first 3 homeworks. So that means actually like today's lecture will not be in the first midterm. Okay, but that's not an excuse to take a nap right now. So I thought that it might be a good time to just like do a summary of what we have done so far, since that's the stuff that's going to be in the midterm. So first we started with an introduction to computer science, and basically what I tried to convince you of is that computer science is no more about computers than astronomy is about telescopes. Now, that's not my quote. It's not clear who said it. Some people say it's Dijkstra, but some people say it's not him. And then after that introduction, we started talking about logic, which is like the foundation of mathematics, which is a good place to start because our language is math. And we'll even see like there's more connections between computer science and logic. We'll discuss more about that in the future. And then we dove right in. We talked about computation, how you formalize computation. We started with the deterministic finite automata, which is a very simple kind of a machine that recognizes only simple kind of languages, regular languages. That was kind of like a warm-up to Turing machines, I guess, but like DFAs also have interesting applications too. So they're really worth studying by themselves. And then we talked about Turing machines, which is the formalization for computation and algorithm. And then once we formalized what we mean by an algorithm, what we mean by computation, the first natural question you can ask is, of course, like, are all problems, computational problems, computable or not? Or are there some problems that are not computable? So we discussed computability in the previous lecture, and we saw here basically that most problems actually are undecidable or uncomputable. And in fact, there are also some very interesting problems, like the halting problem, that's undecidable, uncomputable. But really all hope is not lost. Actually, most of the interesting problems are decidable. After all, when you go on to write a program, usually whatever you have in mind, you can write a code for it and do it. Okay, so if most problems are decidable, then what's the next question that we can ask? The next natural question is computational complexity of a problem. Or you can describe it as the practical computability of a problem. Because you could have a problem that's computable, but maybe it takes like a gazillion years to get to the solution. Well, okay, theoretically it's computable, but from a practical point of view, it's really not computable. And there are so many interesting problems that we want to be able to solve efficiently, right? It can have a major impact in our world. So the study of computational complexity, I don't think I have to really motivate it to this crowd. Okay. Now, what are some interesting questions that we're going to try to address here? So first of all, how do we define computational complexity? What is the right level of abstraction to use? So that's very important in many areas, right? So you want to use the right level of abstraction so you don't get distracted by the little details. How do you analyze computational complexity of problems? What are some interesting problems to study in this context? What can we do better to understand the computational complexity of problems? and so on. So you can ask various interesting questions. We're going to try to tackle some of these. And I guess in this lecture, we're going to start with maybe the first two questions up here, like how do we define complexity and what is the right level of abstraction to use. Okay? And then what is next? So if you remember, these are the 6 Millennium Prize problems, the most important math problems, 7 most important math problems, each having $1 million price tag. One of them happens to be a computer science problem, the P versus NP question, a $1 million question. Okay, or perhaps it's maybe a $6 million question. Okay, so this P versus NP question is like the holy grail of computational complexity theory. And maybe in about 3 weeks or 4 weeks, we're going to precisely understand what this question is. We're going to know exactly what this question is about, what this question is asking, so that you can go on and start working on it. Okay, so and that will be like, so at that point, probably we're going to be halfway through the course. Okay, so let's start with the introduction to computational complexity now. So we can talk about 2 things. We can talk about the computational complexity of a given algorithm, and also we can talk about the computational complexity or the intrinsic complexity of a computational problem. So the second one, the computational complexity of a problem, is basically defined to be the computational complexity of the best algorithm that solves the problem. Okay? And you can ask, well, okay, computational complexity, but with respect to what? So we can look at different resources. Time, the number of steps used. Space, the amount of memory used. Randomness, the amount of random bits used, let's say. Or even you can talk about quantum resources. And we're going to talk about all of these in this course. But today, and for this lecture and the next lecture probably, our focus will be on time complexity, okay? We're going to define computational complexity with respect to time, okay? And recall the Church-Turing thesis, okay? So the Church-Turing thesis basically implied that with respect to computability, the computational model does not matter. Right? You can use Turing machine, you can use a Mac, a Windows machine, you can use Python, Java, whatever. If one problem is computable in one of those models, it will be also computable in another model. Okay? Unfortunately, this is not true, this is not the case with respect to computational complexity. Okay? So here the model makes a difference. Okay? So the first thing I'm going to try to do now is to show you how the model can make a difference. Okay? So how the model can make a difference. And to illustrate that point, we're going to start with looking at what's called a multi-tape Turing machine. Okay? So this is like a Turing machine that we all know and love, but now it has, rather than just one tape, it has K tapes. Maybe it has 2 tapes or 3 tapes, some fixed number of tapes. Okay? And basically, the way it operates is very similar to a one-tape Turing machine. Its transition function now looks like this: delta Q times gamma to the K, and so on. Actually, the details really don't matter. Basically, the point is that whenever you're in state Qi, and you read symbols A1 on tape 1, A2 on tape 2, and all the way up to AK on tape K, what you do is you transition to another state Qj, and then you switch A1 to B1, A2 to B2, and so on, and then each tape head moves right or left. Yes, but again, as I said, the details don't matter too much. Okay, but that's the way it is. And then you can ask, is it more powerful with respect to computability? No. Okay, so whatever you can compute with a multi-tape Turing machine, you can compute with a single-tape Turing machine. Okay, but now let's look at this language, 0 to the k, 1 to the k. Okay, one of our favorite languages. How many steps does a single-tape Turing machine take on this language? Okay, so here's one Turing machine that solves it. Okay, on input string W, so you do basically the obvious thing. Okay, well, the first thing you do is scan the input and then check that the zeros and the ones are in the right place. So you don't see a 1 before a 0. If you do, you reject. Then you repeat while both zeros and ones remain on the tape, and then you scan the tape and then you cross off a single 0 and a single 1. A 0 and a 1, a 0 and a 1, a 0 and a 1. Just keep crossing them off. And then if there's some zeros remain but no ones remain, then it's a reject. And also if there's some ones remain but no zeros remain, then it's a reject. Else you accept. Okay, so very simple algorithm. What's the number of steps here? It's O of n squared, right? Why? So in the first step, you just scan through the input once. That's order n. That doesn't really matter. So the real action is like when you do this repeating step. And there, what are you doing? You're basically crossing off each 0 and 1. Each 0 and 1. There are n over 2 zeros, right? So you have to cross off each one of those. But whenever you cross off a 0, you also have to go all the way to the other side of the tape, cross off the 1, and come back. So whenever you cross off a 0, you're taking n steps, basically, order n steps. And you are crossing off n over 2 zeros. So that's n times n, basically, roughly order n squared. Okay. Now let's look at multi-tape, two-tape Turing machine. Only 2 tapes. Okay, and we're going to, again, do the most obvious thing here. Okay, so let's say these are the 2 tapes. The first one is tape 1, which contains the input being 0, 0, 0, 1, 1, 1. And then we have another tape there. The first step is exactly the same. We just check everything is in the right order. And then what we do is we scan the zeros until the first one and copy the zeros to tape 2. Okay, so the zeros, bam, get copied to tape 2. And then what you do is you just basically scan the ones, and for each one read, cross off a 0 on tape 2. Okay? Now that you have this copy of the zeros, you basically, and you have 2 tape heads, you check if the 0 corresponds to 1, you cross them off, 0, 1, cross them off, 0, 1, cross them off, 0, 1, cross them off. Okay? Because in one step, I can move both tape heads. Okay, and then, you know, if all zeros are crossed off before all ones are read, reject. If all zeros are crossed off, accept and reject. So I mean, it's clear what the accept and reject conditions would be. Okay, so how many steps is this? Order big O of n. Exactly. So big O of n, right? So for each 0, I cross off a 1. Okay, so now we have a single tape algorithm that does it in order n squared, a 2-tape algorithm that does it in order n. Now, can we do it better with a single tape using less steps? Okay, and it turns out that we can do it. Okay, so here is another algorithm. The first step is again the same. And then you do the following, and I'm going to explain this with picture in the next slide, but let's just read it anyway. So repeat while both zeros and ones remain on the tape. What do we repeat? We scan the tape. We check if the number of ones plus the number of zeros. We check the parity of the number of ones and the number of zeros. If it's odd, we reject. Otherwise, we scan the tape and we cross off every other 0 starting from the first 0. And we do the same for 1. We cross off every other 1 starting from the first one. Okay, and we do it that way. So let me actually explain this part in picture. Okay, so I'm skipping the first step where you're checking the zeros and the ones are in the right place. So I'm looking at this part, repeat while both zeros and ones remain. And let's actually come to this part directly. Scan the tape, cross off every other 0 and every other one. So what do? So you start with the first 0, cross it off. This doesn't get crossed off. because you do cross off every other 0, this one gets crossed off. Skip that one, gets crossed off. Skip that one, gets crossed off. And then starting with the first one, cross it off. Cross it off. Cross it off. Cross it off. And then you reach the blank symbol. And then while you're going back to the beginning, now you can actually do this step. Scan the tape if the number of ones plus the number of zeros is odd or not. And that's very easy to do, right? So it's like a DFA can do that. You're just looking at the parity. Okay, so since you're just looking at the parity, you can easily do that. You do this check. In this case, they are even, 0, 0, 1, 1, 1. So we're in good shape. So then we do the same thing. So now we start with this 0, cross it off. This doesn't get crossed off, but this one does. And then start with the first one, cross it off. This doesn't get crossed off, but then this one does. Okay, and then you do the same thing. Okay, so first of all, and it goes on like this, and then you cross off 0 and 1, and then you accept this one. Okay, so it's not obvious why this is correct, why this solves the problem correctly. But first, let's look at the running time, number of steps. What is the number of steps here? Yes, so it's order n log n. Why is it order n log n? Because every time I scan, I'm crossing off half of the letters there, right? So I'm going to repeat this process log n times, because every time I'm getting rid of half of the characters. And every time I scan, that's n steps, at order n steps. So in total, it's n log n steps. And then you can say, okay, why actually does this work? And I do have a slide on this, but you know what? I'm going to skip it. So if you can go home and check this and convince yourself why this works, but that's not the important thing, okay? So the important thing is we can ask now, can we do better? So it turns out that order n log n is the best for one tape Turing machine. Okay? And we had order n for 2 tape Turing machine, and that's the best you can do with a 2 tape Turing machine. Why? Because at least you have to scan the input, right? And that takes order n time. So that's a trivial lower bound. Okay, so keep that in mind. So then we have this difference between 1 tape Turing machine and 2 tape Turing machine. Let's look at the function in Python that now recognizes this language, that solves this problem. Okay? So here's a 2-finger algorithm. So what it does is you have your input. Okay, so you have 2 pointers basically. The first one low starts from the first character. The second one high starts with the last character, and checks, is this a 0 and this is a 1? If it is, then you go to the next one, 0, 1, go to the next one, 0, 1, go to the next one, 0, 1. Okay, so that's what it does. Now, how would you analyze the running time of this? Well, you would probably say, okay, you look at it at each instruction. Okay, let's look at it, number of steps. So this one is like 1 step. This one is like 1 step. While low, less than I, you check a condition there. Let's say it's 1 step. If s low not equal 0 or s high not equal 1, well, that's like, I don't know, 3 steps, 4 steps, 5 steps. Doesn't matter, right? We're going to look at it big O. So some constant number of steps. That's 1 step. That's 1 step. That's 1 step. That's 1 step. And you say, okay, I have, seems like order n algorithm. So you're happy, linear time. It doesn't get better than that. But okay, let's look at this more closely now. Okay, let's look at, for example, high minus equals 1. Well, initially high is n minus 1, okay, which is the length of the input minus 1. So how many bits do you need to store high? You need about log base 2 of n bits. Okay. Now let's say that high n is a power of 2, and let's say n minus 1 is a power of 2, so high is like 1, 0, 0, 0, 0, 0, 0. And you say, okay, I subtract 1, and now it's like 0, 1, 1, 1, 1, 1. So is that really one step? That seems like log n steps, no? Log base 2 of n. And it's okay, well, so this step, maybe it's really like log n steps. And in that case, then maybe the running time is n log n, or the n log n. Okay, so let's look at another part of this code. If s low not equal to 0, s high not equal to 1. Initially, low is 0, high is n minus 1. And then you can ask, well, okay, I check s low, s0. Okay, does it take like n steps to go from s0 to sn minus 1? Well, in a Turing machine, that would be the case, right? If you want to go from the first character to the last character, you would need like n steps to do it. So say, okay, so is this like n steps now? So now it's like order n squared? Right, so that's like, we had this cool like linear time algorithm, and now like we're not even sure if it's like linear or quadratic or what. Okay, so basically the point here is that all of these examples, number of steps, the running time depends on the model you choose. Okay, and then you might ask, okay, what is the right model then to choose? What's the model that we should choose? Well, I mean, there's no like best model, definition of best model, but there are two important things. The first one is that when you do running time analysis, first of all, you have to be clear about what your model is. Okay, otherwise, I probably don't know what you're talking about. The second one is all reasonable deterministic models seem to be polynomially equivalent. So in a sense, you could say, well, it doesn't matter too much because they're polynomially equivalent. But at the same time, it does matter because there is a difference between an order linear time algorithm and a quadratic time algorithm. Okay, but you know, again, it's something to keep in mind. Okay, so if we come back to this, and this is like you probably how most of you would like do the runtime analysis for a function like this, which is like order n linear time, you can ask, well, what does this correspond to? Which model does this correspond to? And this basically corresponds to what we call the RAM model, which is the random access machine model. Okay? And it's a nice model. It's a good combination of basic reality and simplicity. Okay, so in this model, basically, I'm not going to get into the details. I'm not going to formally define it. All you need to really know about this model is that these basic operations like plus, minus, division, multiplication, less than, greater than, these basically take 1 unit time, we assume. Okay, so like 2,445 times 12,894, that's 1 unit. And the other important thing is, if you want to access a particular memory location, like an element of an array or a list, that takes also, we assume, 1 unit of time. Now, the second one is a good assumption. Actually, this corresponds to the machines that we use today. So in those machines, we can access memory locations in 1 unit of time. So that's more realistic. Now, the first one is a bit tricky. Okay? So we have to make a note about this. So this is a good model when you say you're working with like just integer data types, maybe like you're using maybe 32 bits to represent them or 64 bits to represent them, I don't know. Right? So you have some finite amount of space reserved for these numbers, and you say, you know what, all the numbers that I'm going to deal with, they're never going to exceed 64 bits. So all my operations are going to be on like 64-bit integers, numbers. So in that sense, it's okay to say, okay, this is just 1 unit time. Okay? Because it's a finite fixed length. But it's not really a good model when your numbers can grow. And when you're interested in doing computation over, let's say, 1 million digit numbers. And this happens, okay? So like, in various different areas, you want to be able to do computation on humongous big numbers, okay? And in that case, when you're like dealing with like 1 million digit numbers, it's of course not reasonable to say, well, it just takes one time to multiply them. Okay? So the point is that this is a good model. You can use this. So in fact, this is what we're going to most of the time use. We're going to have the RAM model in mind, but with the understanding that if we ever really want to work with big numbers, then this first one, the multiplication plus these basic operations, we're not going to assume they take 1 unit of time, and we're going to do a proper analysis on those operations. Okay? Any questions? Okay. So now, now that we know like how the model can make a difference, let's try to define the time complexity of an algorithm and the intrinsic complexity of a problem. Okay? So first, recall these definitions we had from before. So we said the computational problem P is just a function that maps sigma star to sigma star, words to strings, and the input is called an instance, the output is called a solution. We've been dealing a lot with decision problems where the output is just 0 or 1 or yes or no or accept, reject. And an algorithm solves the problem P if it outputs the correct solution on every instance, right? Okay, so now defining the running time of an algorithm. So with a specific computational model in mind, right? So because the model is important, you can say the running time of an algorithm, A, is a function T sub of A, which maps positive naturals to positive naturals, and it's defined as follows. T of A of n is basically the maximum number of steps that the algorithm A takes on instance I, and the maximum is over all instances I of length of size n. Okay, so this max is the worst case. We're looking at the worst case running time. We're looking at the worst case running time. And often we're going to drop this subscript A from the notation and just write T of n when the algorithm is clear from the context. Okay? And also remember that n always denotes the input length. Okay, so any question about this definition? Yeah?
So by input length, you assume that all numbers are stored in constant encoding?
If, which numbers?
So the numbers you have on the input are all have constant length.
Right, so it depends on exactly the model. This is why with a specific computational model in mind. So you might say, oh, I'm just going to deal with constant length numbers. In that case, you can just assume they have constant length. Or that might be an important factor, and then you don't assume that. Yeah. Okay. Now you might ask, why worst case? Okay, so let's just address that question very quickly. Well, first of all, like we're not very dogmatic about it. So we do study average case complexity, which is like you look at you pick a random input, and you look at the expected running time of your algorithm. So that's an area that people study. You can try to look at typical instances, whatever typical means. You can try to do smooth analysis, which is something in between worst case and average case, and so on, right? So you can try these things, and no one will stop you from doing it. But at the same time, worst case analysis has a special place in our hearts. Okay, so it has its advantages. So first of all, it's like an ironclad guarantee, right? It's worst case guarantee. When you say that your algorithm runs in order n squared time, it runs in n squared time no matter what the input is, right, of length n. So that's always a good thing to have, a good guarantee to have. It matches our worst case notion of an algorithm solving a problem. Like when we say an algorithm solves a problem, we don't mean like it solves it on some instances. We mean that it solves it on every instance, right? So it matches that. And there's some problems. You can see some problems with the other approaches. You can say, well, if you want to look at typical instances, well, how do you define typical? It's not clear. Random instances, if you're looking at like average case, well, they may not be representative of the problem. Okay, so these have their own downsides. And another like important upside of worst case analysis is that it's easy to analyze. The math is clean, and you know we can really build a nice, good theory based on worst case analysis. Okay. Okay, so that's why we look at worst case usually, and then we can try to define now the intrinsic complexity of a problem. And again, with a specific computational model in mind, maybe you can say, okay, the intrinsic complexity with respect to running time of a problem P is defined by the minimum overall T of A algorithms A that solve P. So they basically the time of the best algorithm that solves P. So, yeah, anyone have a question here about this definition? Yeah.
Is there a way to determine the intrinsic complexity without finding the specific algorithm?
Well, there might be. I mean, it's hard to imagine how you can find an upper bound on.
Given a specific algorithm, is there a way to prove whether or not it's the best one?
Okay, so we're going to discuss this. Yeah. So. You have to come up with an upper bound and a lower bound, but I'm going to come to this actually. But like no one is like, everyone's happy with this definition? Yeah?
Yeah, how do you know the completeness set of algorithms A that solve P?
Say again?
How do you know the completeness of the set of the algorithms that solve P?
How do I know the completeness of the algorithm? Well, I mean, I don't know what you mean by completeness, but like I assume I go over all the algorithms that solves it.
Well, how do you know that there are no other algorithms that could possibly solve it?
But this takes into account all of them. So just by definition, I guess, I'm going through all of them. Yeah. But that's not really a problem. So no one, everyone's happy? Yeah.
Yeah, so I think you can't actually use algorithms, but actually the problem itself to determine the complexity is you might not be able to find an algorithm, but you know that you can't possibly solve the problem less than some lower bound, but you might not find an algorithm for that lower bound.
Well, okay, so this definition says nothing about our ability to find it or not. This is purely theoretical. I'm looking at all the problems, algorithmic space. So, okay, so the problem, okay, I don't want to spend too much time here. So the question here is like, you're taking the minimum over functions. How do you compare functions? How do you say one function is less than another function? Okay, so what does that really mean? So would you say n squared is less than or equal to 100n because, well, I plug in n equals 1, n equals 2, n equals 3, and so on, 100n seems bigger. Right? So it's not clear how you compare functions. Okay, so what we're going to do now is actually exactly discuss this, and we're going to talk about the computer science way of comparing functions. The big O notation, the big omega notation, and the theta notation. Okay, so and big O basically corresponds to like less than or equal to, omega is greater than or equal to, and theta is equal to. Okay, so I mean, without a doubt, this is like the most important notation in computer science, right? So you really have to be very comfortable with this. Now, I know that all of you at least have some intuitive understanding of what big O is. But I also know that not all of you have actually seen the formal definition of what big O is. Okay, so we're going to see the formal definition. So if you have already seen the formal definition and everything, well, just bear with me. for this part. Okay, so big O, starting with big O, is basically our notation for less than or equal to when comparing functions. Okay, so of course when we are defining this less than or equal to, we have in our minds that these functions are not just arbitrary functions, mathematical functions, but these actually correspond to running time of algorithms, right? So they correspond to the time complexity of algorithms. So with that in mind, we want to use the right level of abstraction. We don't want to get tangled up in details. We want to use the right level of abstraction that's useful. And we want to basically hit a sweet spot here. Okay, so what's the sweet spot we're looking for? First of all, it should be coarse enough. Should be coarse enough to suppress details like programming language, compiler, architecture, and so on. Okay, so we don't want to develop a theory, one theory for Windows machines, another theory for Mac machines, and so on, right? So we want something that's coarse enough that these kinds of details don't matter. At the same time, we want it to be sharp enough so that we can actually make meaningful comparisons between different algorithmic approaches. Meaning, like, if there's one algorithm that's really better than another algorithm, then our notation hopefully actually captures that difference. Okay? And big O, we are very confident does that. Okay? So for example, if you write something like the running time is 8n squared minus 3n plus 84, this is like having too many significant digits. Okay? So this is too much information in some sense. And what we do here, we say, well, this is just order n squared, right? So when we write big O of n squared, there are two things to keep in mind. The first thing is that we don't care about constant factors, right? Because even a change in the alphabet size in a Turing machine, if you go from an alphabet size of 3 to an alphabet size of 4, that's going to affect the running time by a constant factor. We really don't want to factor this into our notation. Now here you might say, well, what if the running time is 10 to the 20 n squared, and then you're just saying that's order n squared, and like you're getting rid of that huge constant there. Well, yes and no. So experience shows that if you have an algorithm that's like 10 to the 20 n squared, well, first of all, experience shows those kinds of algorithms don't really show up. You don't really see that kind of big constants. But if you do see big constants, usually then you can apply whatever programming tricks you have and get that constant down to some reasonable value. So this doesn't really is a big problem, big concern for us. Okay? But that being said, constants in the real life, when you're going out there, do matter, right? So like when you have an algorithm that runs in 100 n squared time, for sure, go ahead and try to optimize the constant. But from a theoretical perspective, we're not worried too much about it. Now, that's the first thing. Don't worry about constant factors. And the second thing is we don't care about small values of n. Okay, why we don't care about small values of n? Because they're not interesting. When the input size is small, input length is small, do whatever you want. Run an exponential time algorithm if you want. Those are not the interesting instances. The interesting instances are like when the big instances. So we really want to know the performance when n is large. Okay, so informally, big O is an upper bound that suppresses constant factors and ignores small n. And here's a little note about suppressing constant factors. So if big O suppresses constant factors, then it also suppresses lower order additive terms. Right? So that's easy to see. So let's say we have n squared plus 100 n plus 500. We say that's n squared, order n squared, because we say, well, 100 n plus 500, those are small order additive terms, and they get suppressed. Why? Because, well, you can say, 601 n squared is big O of n squared because we don't care about constant terms. Right? But 601 n squared is n squared plus 100 n squared plus 500 n squared. which is strictly greater than, if you look at term by term, n squared plus 100 and plus 500. So if 601 n squared is order n squared, then of course also n squared plus 100 and plus 500 should also be big O of n squared. Okay, and you can look at the graph of this. Here and the x-axis I have n going from 0 to 1,000, and the y-axis is t of n. You can see they're pretty close. And now if I look at n when it's like from 0 to 10,000, you see like these functions n squared and n squared plus 100 and plus 500, very close. Okay, so again, informally, we're saying for functions f and g, we say f of n is equal to big O of g of n. This roughly means that f of n is less than or equal to g of n up to a constant factor and ignoring small n. Okay, so far, hopefully you basically all know this much.
Big O notation represents, formally represents a set, right?
I'm going to make a comment on this. Yeah, I'm going to make a comment on this later. Okay, so here's the formal definition. Oh, yeah.
Why are F and G from naturals to reals?
I mean, it could be from naturals and naturals as well. Doesn't matter, yeah. Or it could be, you could define it for reals to reals as well. But I'm just trying to keep it simple. And for which one?
For the running time?
Yeah. But you can define big O notation for more natural numbers, not just for n to n, but from real to real. There's a way to do that too. Okay, so here's the formal definition, if you haven't seen it before. Okay, so we say that f of n is big O of g of n if there exists two constants, capital C and n naught, bigger than 0, such that f of n is smaller or equal to c times g of n for all n bigger than n naught. Okay, so a constant c and n naught means that they cannot depend on n. So what this really means is that f of n is big O of g of n if you can find a constant such that when you multiply that constant with g of n, then c times g of n is bigger than f of n. Okay, and we just care about numbers n greater or equal to n naught. So we only care asymptotically. Yeah.
Shouldn't be n not greater equal to 0?
And not greater or equal. Maybe it's just small technical. I don't think it's very important. Yeah. Okay. So that's the precise mathematical definition of this. Here's a little graph. So you might have your red function is f of n, and you want to say f of n is big O of g of n. But you look at g of n, it looks like, well, it's below f of n. But at the same time, if I multiply g of n by 2, then I am able to get it above g of n, and it's above g of n after this point n naught. Okay, and then here's an example. F of n equals 3n squared plus 10n plus 30, and g of n is n squared, and you can say f of n equals order big O of g of n. Okay, and if you wanted to prove this, if we said prove this fact, f of n is order g of n, what you need to do, you need to provide the c, the constant c and n naught. Okay, and we say, okay, for example, take c to be 4 and naught to be 13. And then you say, well, with this c and this n naught, you can say f of n, which is 3n squared plus 10n plus 30, is less than or equal to c times g of n, which is 4 times n squared, when n is more than or equal to 13. And you can check that this is true. So when you're proving big O stuff like this, it might help to think about it as a game you play with an adversary. Okay? So when you're proving f of n is order g of n, you can say, okay, I'm playing a game against an adversary, and here's the game. So what you have to do, you go first. And what you have to do is you have to provide two constants, c and n0, absolute constants, maybe 5 and 100 or whatever. And then its adversary's turn, and the adversary picks some n, which has to be bigger than this n naught that you provided. And then you will win if f of n is less than or equal to c times g of n for these values, c n naught and n. And your goal is basically to have a winning strategy, a strategy that will make sure you always win. So some constants, you have to pick some constants, c and n naught, so that no matter what the adversary picks for n here, you always win. Okay, you're guaranteed to win. Okay, so it can help to think about it this way. Okay, so here's some examples. So 1000n is big O of order n because we don't care about constants. 0.00001 is order n. We don't care about constants. 0.1n squared plus 10 to the 20n plus 10 to the 10,000 is order n squared. So n is big O of 2 to the n. So sometimes some students get confused about this, like n is 2 to the order of 2 to the n. Yes, so the big O notation records an upper bound. Okay, so n is obviously much smaller than 2 to the n, so you can say n is big O of 2 to the n. 0.0001 n squared is not big O of n. N log n is not big O of n because this log n factor here is not a constant. It grows with n. Now when we write log base 9 of n is order log n, note that when we say big O of log n, we don't have the base there. So why don't we have the base? We don't write the base because you can go from one base to another base through a constant factor. So if you have log base p of n, that's log base k of n divided by log base k of b. This part is a constant. So you see that you can go from one base to another base using a constant factor. So that's why when we say like order big O of log n, we never put the base there. We don't put log base 2 of n or anything because it doesn't matter. 10 to the 10 is big O of 1. Okay, so we could have said it's big O of 10, big O of 500, but we, by convention, we just say big O of 1. And maybe this is coming to your question now. So a little note on the notation, people usually write 4n squared plus 2n equals big O of n squared. I don't really like it that much, so I think it's better to write it as 4n squared plus 2n is included in order n squared, because you should really think of big O of n squared as like a set of functions that are big O of n squared, and you're saying, well, 4n squared plus 2n, belongs to this set of functions, which is big O of n squared. But people more often use this notation. Okay, so let's look at runtime scaling of some of these functions, and maybe this will be another sort of justification for ignoring constant terms in the big O. Okay, so if you have a function that has running time c times n, and you double the input, the running time, the number of steps becomes c times 2n, okay, and that's a ratio of 2. If you have a function that's, if you have an algorithm that runs in c n squared time, you double the input, then you have c times 2n squared, and the ratio there is 4. So you see that the ratio does not depend on c, the constant. Okay, cn cubed, the ratio is 8. If you have some polynomial n to the k, the ratio is 2 to the k, but still a constant. If you have a function like 2 to the n, you see that the behavior changes quite a bit. You double the input, the running time becomes c times 2 to the n. The factor here, the ratio is 2 to the n. Now it depends on n, it depends on n exponentially. In essence, the running time is being squared, if you look at it, when you double the input. And that's a totally different behavior than polynomial. Okay, so you know all these big O classes and their names. And then you look at the graphs of these important big O classes, 2 to the n cubed, n squared, 104 square root of n log n. Who knows what happens for small n? We don't care, but after a while, we see that 2 to the n dominates n cubed dominates n squared dominates n, and dominates square root of n, and that dominates log n. Now, let me make a point about the difference between n and log n, because this is very important to understand. Okay, so how much smaller is log n compared to n? So let's make a table. So when log n is 1, n is 2. When log n is 3, n is 8, because 2 to the 3 is 8. 2 to the 7 is 128. Okay, so when log n is 10, we're already in the 1000 for n. When log n is 20, we're in 1 million. When log n is 30, we're in 1 billion. When log n is 60, we are in 1 quintillion range. Right? So 60, I mean, is really like nothing, peanuts. And while 1 quintillion is 1 quintillion, right? In fact, if I go say log n is 300, okay, then the corresponding number is going to be 2 to the 300, which is like the number of atoms in the observable universe. So think about that difference, okay? 300, as I said, is like peanuts. And then you have 2 to the 300, which is like the number of atoms in the universe. Okay, so you should really think about that difference. And this difference, of course, is exactly the same difference between n and 2 to the n. Right? So they have the same relationship. Log n is the inverse function of 2 to the n. So this suggests that if you have an algorithm that runs in exponential time, okay, exponential like 2 to the n, right? So run away. Okay, so this is bad news. Okay, so there's no hope of being practical because, as I said, even if n is like 300, like you're in big trouble. Okay, so here's a very small example of an exponential running time algorithm. So suppose you're given a list, an array of integers, and you want to determine if there's a subset of the integers that sum to 0. Okay, so maybe something like this. Is there a subset of these integers that sum to 0? Yes. If you take -3, -2, and 5, that sums to 0. Now here's an algorithm, naive algorithm that solves this. Exhaustive search or brute force search. Okay? Try every possible subset. Well, how many subsets are there? 2 to the n. So this is going to take at least 2 to the n steps. Okay, so no hope of being practical whatsoever. Even when like the input is n is like 100, 150, you know, the universe will degenerate into black holes and radiations before you get an answer. Okay. So the way to think about these functions is basically log n is like super duper smaller than square root of n. Square root of n is really smaller than n. N is somewhat smaller than n log n, but not much smaller. And then n log n is like really smaller than n squared. N squared is really smaller than n cubed. And then like n cubed is like super duper smaller than 2 to the n, which is like super duper smaller than 3 to the n. And then I mean, this is something we're going to discuss actually in the next lecture, not this lecture. But let me just say anyway, you know, and you probably know, where's the theoretical divide between efficient and inefficient? So we say that if the running time is not order n to the k for some constant k, if it's not like polynomial complexity, then we consider it to be inefficient. Yeah, but you're going to say, well, wait a minute. If it's like n to the 100, how is that, how is that considered efficient? Yeah, we're going to discuss it. We're going to have that discussion in the next lecture. Okay, so here's some exotic functions. Not these ones. These are the ones we know. But it's good to, be aware of that there are some exotic functions in between these functions. So between 1 and log n, you say, well, is there any function that can come up, that naturally comes up? Well, actually, log n, you will see it come up from time to time. Okay. And you can say, well, is there anything like between 1 and log n? And you say, well, okay, well, you can go triple log, I guess. And sometimes that even comes up. I've seen it. But like, there's another interesting one, which is log star of n. So this is like, remember like log n, you can define it as the number of times you need to divide n by 2 to get it below 1. Log star of n is defined similarly. It's the number of times you need to take log to get the number below 1. Now, for all like practical purposes, this is a constant. Okay, so you can think like, if I want to make the log star of n like 10, let's say, what's the number that I have to start with? What's n that makes log star of n 10? And you know, you'll arrive at this pretty big number. Okay, so you can say now, between n, like a polynomial, and 2 to the n, there are some functions, interesting functions, like n to the log n. Okay, so n to the log n is not a polynomial because the exponent is not a constant, but it's also not really exponential because the exponent is not really n, okay, or big O of n. So, and that kind of running time also comes up. Now, is there anything bigger than 2 to the n? Well, of course, there's like 3 to the n and k to the n. But what about like bigger than k to the n? Very good. So n factorial is definitely bigger than these numbers. Anything bigger than n factorial? Yeah. All right. So, well, I was thinking like n to the n would be like the next step here. And then you can say, well, 2 to the 2 to the n. And then, 2 to the 2 to the 2 to the, like n times. And actually, this function, the last one there, is the inverse of log star of n. Okay. And then, these, you might say, oh, this must be it. There cannot be anything other than this. But here's an interesting fact. The fastest algorithm for multiplication two numbers, n times log n times 2 to the order log star of n. Okay, so we're going to discuss multiplication later. And then we have big omega, which is like big O, but like in the other direction, greater or equal to. So it's an upper, so big O was an upper bound that suppresses constant factors and ignores small n. Big omega n is a lower bound that does the same thing. Okay, and here's the formal definition. It's very similar. Again, you need two constants c, now small c and n naught, such that you can multiply g of n with the c to make it smaller than f of n, and of course for n bigger than n naught. Okay, so here's f of n. You say, oh, g of n looks bigger, but I multiply it by half. Then I see that after a point n naught, it is smaller. Okay, so 10 to the minus 10 n to the 4 is omega n cubed, obviously. Now, this one, 0.001 n squared minus 10 to the n minus 10 to the 30 is omega n squared. But it's also big O of n squared too, right? And that's okay. So something can be big O of something and also omega of that thing. Right? Something can be less than or equal to something and also greater and equal to something. But when that happens, what do we say? Those two things then we say are equal. So actually, that's the next thing I'm going to discuss. But anyway, so n to the 0.001 is omega log n. So any n to the c, whatever c might be, is always a faster growing function than log n. And for similar reasons, n to the 1.0001 is omega n log n. And theta is basically the equality in this family, right? So the formal definition is, f of n is theta g of n if it is big O of g of n and also big omega of g of n. And you can check, that this definition is equivalently can be written like this. Okay, so now you need three constants, small c, capital C, and n naught, and you want to be able to sandwich f of n between small c times g of n and capital C times g of n for n bigger than or equal to n naught. Okay, so back to intrinsic complexity now. So then we can define the intrinsic complexity with some specific computational model in mind. to be the complexity of the most efficient algorithm solving it. And how are we comparing now the efficiency of algorithms? We are using the big O notation. Okay. So if you give an algorithm that solves a problem, okay, that gives you an upper bound on the intrinsic complexity of the function, right? You're saying that here's a way to do this problem in this much time. Now, there could be a better algorithm that does it, so maybe the intrinsic complexity is even smaller. So that's why it's only an upper bound. And now you can say, well, if I want to really nail down the intrinsic complexity of a function, I better also provide a lower bound for it. Well, okay, so how do you show a lower bound on the intrinsic complexity? This is usually a much harder task. So you have to argue against all possible algorithms that solves it. And the space of all possible algorithms is humongous. Okay, so there are various tricky, interesting, clever ways you can solve a problem. So how do you argue against all of those possible ways of solving a problem in one shot? So a very common kind of mistake is, when you're trying to solve, when trying to prove a lower bound is, well, you start your argument by saying, well, any algorithm that solves P, problem P, must do blah. Well, that's 99.999% of the time is a wrong argument. So how do you know it must do blah, right? So it could do anything. So never start your argument saying that, oh, any algorithm that solves this problem must do something. Okay? And the dream here is, of course, to get matching upper and lower bound, but this is usually a very hard task. Okay? So here's, but sometimes you can do it. So, for example, in this one, the two-finger algorithm that we looked, in the RAM model, we saw that it's order n. And it's easy to show that, you need also at least omega n for this, right? Why? Because you need to scan the input to determine it. But, so you can ask, is there a faster algorithm, n over log n? Well, there's not going to be one. That being said, you should be formal about it. So you can say, well, any algorithm L must use at least n steps, and here's the formal proof. Suppose there is an algorithm A that decides Ln less than n steps. Let I be the instance A to the k, B to the k. So that's a yes instance. But since we have less than n steps, when A runs on input I, there must be some index j that A never reads, that A never accesses, right? So you say, okay, I'll take that index j, I will flip it, okay, and I prime is going to be that that instance with the j coordinate flipped. Now I prime is a no instance, but you say, well, algorithm A behaves exactly the same way because it doesn't access the jth location. It behaves exactly the same way as it does on I and I prime. But one is a yes instance, one is a no instance, and that's the contradiction, and that's how you can argue about this. Okay, so this shows that the intrinsic complexity of L is omega n, and we also know that it's big O of n because we have an algorithm that does it in big O of n. So this shows that the intrinsic complexity is theta of n, and we have, whoa. So that's the dream. Okay. Now, the last thing really I want to talk about is being careful about the representation of the input, okay? Because this can also make a big difference in the running time analysis, okay? And I'm going to illustrate this point with just a simple example, okay? So technically, how you represent the input, how you encode the input can make a difference, okay? And as a general rule, the problem description should normally have the encoding, how you represent the input, as a part of the definition of the problem. But if it doesn't, then you should assume by default that it's the minimum number of bits that you would need to represent that input. Okay, so here's an example. Multiplication. So you have two numbers, s and t, and you're looking at the product of s and t. Okay, and then let's say in the problem description it says you could, first of all, so the obvious algorithm that we're going to use is just like multiply s and t by adding s to itself t times. Okay, so that's our algorithm. Straightforward algorithm. Now you say, how do you represent the input? Maybe you represent it in, let's say, unary. Let's try it in unary. So you say s is just like 1, 1, 1, 1, s many ones, t is like t many ones. Okay? So then the input length is an s plus t, right? What's the running time of this algorithm? What's it? S times t, or big O of s times t, right? Because that's basically the number of ones you're going to have to produce as the output. This is order s times t. In terms of n, what is this? Well, you know, s can be like n over 2. T can be like n over 2. So that's like order n squared. So you say, well, good, like we have a quadratic time algorithm. That seems nice. Okay, so now let's look at the same problem, the same algorithm, but now we represent s with the binary representation and t with the binary representation. Okay, so n, the length of the input is log base 2 of s plus log base 2 of t. Okay, and then you say, now I'm going to add s to itself t times. How can I add s to itself in binary? Well, you can sort of use the, you know, grade school algorithm that you use for that. Okay, so you just go coordinate by coordinate. You add each coordinate one by one. You keep track of the carry, and that's how you add it. That's log s time, log s steps, right? Because the s has log s length. But you have to do this t times. I'm adding s to itself t times. So then you say, well, the running time is order t times log s. Okay, so what is this in terms of n? So let me make it easy. So s could be like 1, let's say. And basically t is the other n minus 1 bits. Okay, so in that case, log s is nothing, like a constant. But what is t? T is like the remaining n minus 1. The value of t is like 2 to the n. So this is order big O of 2 to the n algorithm. Okay, so this algorithm actually sucks. Okay, so this is really bad algorithm. So here is a very, very important point. Okay, so when we're dealing with problems with integer inputs, so that might be like multiplying two numbers, adding two numbers. That might be like checking if a number is prime or not, or factoring a given prime number, factoring a number, given number. When you're dealing with such problems, you have to have the mindset that these numbers are like numbers, potentially numbers with like 1,000,000 binary digits. Okay, 1,000,000 digits long. So really, if you look at it, so these numbers have magnitude like, if it says 1,000,000 digits, like 2 to the 10 to the 6. Like, that's a humongous, it represents a humongous number. But like writing it down is not a problem. I just write 1,000,000 digits long. I can definitely do it in a computer. And I can definitely add these numbers up, multiply these numbers, and so on, no problem. But you should always have the mindset that when you're doing operations on numbers, these numbers can be really, really big. Okay? So this algorithm that we described, there's no way it can handle, like, let's say, 300-digit numbers. Okay? Well, there's no way it can do it. So that algorithm sucks, but is there an efficient way to do it? Well, of course, right? So we multiply big numbers all the time. So for example, the grade school algorithm that you learned basically takes order n squared steps to do. And actually, we're going to discuss this next time. And there's actually a much faster way to do this. Can we do better? So we're going to discuss this in the next lecture. Actually, give me 2 more minutes and let me do this too. Strong Church-Turing thesis, okay? So we know the Church-Turing thesis, the intuitive notion of computable, is captured by functions computable by a Turing machine. We talked about the physical version of it. Now there's actually another version of the Church-Turing thesis, which is the strong Church-Turing thesis, which says the intuitive notion of efficiently computable is captured by functions efficiently computed by a Turing machine. Okay, so this seems to be true for deterministic models, no problem. But there was, in the 70s, a challenger to this Turing thesis, which was randomized computation. And it seemed like we can solve some problems much faster than much faster with randomized algorithms than with deterministic algorithms. But then we did some research, and then now we believe that no, like randomized algorithms don't give us any power. Second main challenger, quantum computation. It seems to us now that quantum computation perhaps gives us more power. And in light of the research we've done, we no longer believe the strong Church-Turing thesis and that quantum computers are indeed faster than regular Turing machines. And these are both models, the randomized model and the quantum model, are models that we're going to discuss in this course. So basically, the point is you have to challenge all ideas, even ideas like P different from NP.